Hello there, and welcome to the Sleepy Science Channel. Tonight, we drift into a world so small, it can rest on your fingertip. It's so powerful, it can build entire ecosystems and even alter the course of life on Earth. We are exploring the miraculous world of seeds, not just as tiny beginnings, but as remarkable vessels of patience, resilience, and quiet ingenuity. Within each one lies a story waiting for the right moment to unfold. Some travel across oceans without a map. Others wait through years of cold or fire, holding their breath until the world changes in just the right way. They are carried by wind, by water, and by animals who are unaware of their important role. And somehow, from something so still, an entire living structure can emerge. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there is nothing you need to do. Let your shoulders soften and allow your breathing to slow. And as the day begins to gently fade away, join me as we explore this remarkable world together. Let's begin. A seed can sleep for centuries, then wake with water. That is not poetry. It is a real survival strategy. A seed can remain alive in a state of suspension for astonishing lengths of time, holding its breath through drought, cold, darkness, and long stretches of apparent silence. Then one day, moisture reaches the tissues inside, chemistry restarts, and the waiting ends. One of the most famous examples came from ancient date palm seeds recovered near the Dead Sea. They had been buried for around 2,000 years, yet one was coaxed back into growth in modern times. That kind of endurance changes how we think about life. It means a plant can send its future far beyond its own lifetime. It can outlast storms, kingdoms, and entire landscapes. What looks like a dry speck in the hand may actually be a living pause button, ready to resume a story that began long before anyone alive today was born. Every giant forest begins as something small enough to lose. That contrast is one of the most astonishing things in nature. A towering tree can weigh many tons, cast deep shade, house birds and insects, and reshape the soil beneath it. Yet its beginning may have been so small that a child could drop it without noticing. In that tiny package sits the power to raise a trunk, branch into the sky, and feed whole communities of living things for centuries. Oaks, redwoods, beeches, and pines all begin at a scale that seems almost absurd compared with the worlds they later create. A forest is not just a collection of trees. It is shelter, rainfall influence, carbon storage, fungal exchange, and habitat woven together across time. And all of that can start with something that fits on a fingertip. Once you feel that contrast, seeds stop seeming ordinary. They become one of nature's most dramatic acts of compression, where almost unimaginable size begins in near invisibility. Inside each seed, a whole future plant is folded away, not as a vague possibility, but as a physical structure already taking shape. Within that small body sits an embryo with the earliest version of root, stem, and first leaves prepared in miniature. It is not a blank lump waiting to become organized later. It is more like a tightly packed traveler carrying a map, a ration pack, and the first tools needed for arrival. When conditions turn favorable, the root usually emerges first and pushes downward into darkness. The shoot follows and begins the climb toward light. In many species, the first seed leaves appear before the true adult leaves, helping the young plant bridge its most vulnerable days. This is one reason seeds feel so astonishing when you look closely. They are not merely containers of life. They are compact blueprints already translated into living tissue. A field of seedlings is not a sudden miracle from nowhere. It is an army of hidden plans finally unfolding. The oldest seeds ever grown were buried for millennia. That fact feels almost like a message crossing time. Ancient seeds have been discovered in dry caves, tombs, and archaeological sites, preserved by conditions that slowed decay to an extraordinary degree. Most famous are old date palm seeds from the region around the Dead Sea, including one that later sprouted after roughly 2,000 years. Imagine what that means. A living structure formed in the ancient world remained intact through empires, languages, migrations, and inventions, beyond anything its parent plant could ever have encountered. Then, with modern care, it resumed growth. Not every ancient seed can do this. Age, moisture, heat, and damage usually win in the end. But the rare successes reveal something breathtaking about the durability of dormant life. A seed is not only a beginning aimed at the future. It can also become a biological archive, carrying traits from lost landscapes and older populations into the present with astonishing patience. Some seeds wait for the exact season, temperature, and light. That patience is part of their intelligence. A seed does not simply wake because time has passed. In many species, it responds to a careful combination of signals that helps reduce the risk of sprouting at the wrong moment. Some need winter cold before they will trust the return of warmth. Some seeds only start growing when the difference between daytime warmth and nighttime coolness feels like true spring near the surface. Others are sensitive to light itself, which can reveal whether they are buried too deeply or have finally reached a better place to grow. This matters because germination is dangerous. Once a seed begins, there is no safe return to dormancy. A false start can mean death by frost, drought, shade, or hunger. So waiting is not passivity. It is selection, testing, and restraint. The tiny seed is sampling the world and asking a hard question before it commits. Is this truly the moment to begin? Plants packed food, armor, and instructions into one living capsule. That is one of the greatest design achievements in the natural world. A seed contains genetic instructions for building the next plant, but those instructions are not left exposed. They are wrapped in protective layers and supplied with stored resources that can support the embryo through its first critical stage. In many seeds, that reserve comes as starch, oil, or protein, packed away before dispersal. This matters because a new seedling cannot photosynthesize much at first. It needs a temporary allowance, a starter fund that lets it push out a root, lift a shoot, and begin life before it can feed itself properly. The protective coat adds defense against drying, impact, and attack, while the internal tissues hold the plan for what comes next. All of that fits into something that can be carried by the wind or dropped from a hand. It is hard not to marvel at the efficiency. Life learned to travel light without traveling unprepared. Seeds can travel by wind, water, fur, feathers, and guts. Plants cannot walk, yet their offspring can spread across astonishing distances through the bodies and movements of other forces. Wind lifts dandelions, orchids, and countless drifting seeds into open air. Water carries coconuts and mangrove propagules along coasts and across sea channels. Fur catches hooked burrs that ride unnoticed on mammals until they drop elsewhere. Feathers do the same for birds moving between wetlands, forests, and fields. Then there is the less glamorous method, but one of the most effective. Many fruits are built to be eaten. Their soft flesh attracts animals, while the tougher interior survives the journey through the digestive tract and comes out with a fresh deposit of fertilizer. That means a bird, fox, elephant, or bat may become an unwitting courier for the next generation. Once you notice this, landscapes look different. Movement is happening everywhere. Plants are not rooted to one place in the long story. Their seeds are travelers. Some seeds survive fire, then use smoke as a signal. That sounds almost impossible, because fire seems like the end of life rather than the beginning of it. Yet in some ecosystems, burning is part of the rhythm that makes renewal possible. Certain plants produce seeds tough enough to endure the heat or remain protected in the soil nearby. After flames pass through, the world above them has changed. Shade is reduced. Competitors are gone. Nutrients from ash may be newly available. And smoke itself can contain chemical cues that tell dormant seeds the moment is right. In fire-shaped landscapes such as parts of Australia, South Africa, and California, this timing can make all the difference. Waiting for a burned landscape is not reckless. It is strategic. The seed is not simply enduring disaster. It is reading the aftermath as opportunity. That turns wildfire into something more complicated than destruction alone. For some plants, it is also the opening note of a long-awaited beginning. One tiny seed can remake a field, a forest, or history. Sometimes the change is ecological. A single seed that lands in the right gap can grow into a tree that shades the ground, draws in birds, feeds insects, alters soil moisture, and eventually helps many other species settle around it. Sometimes the change is human. The spread of wheat, rice, and maize seeds transformed diets, settlements, trade, and power on enormous scales. A handful of planted grains could mean stored food, permanent villages, larger populations, and the slow rise of civilization as we know it. There are darker versions too. Seeds of invasive plants have crossed oceans in cargo, mud, or contaminated feed, then reshaped habitats with startling speed. So the scale of a seed can be misleading. It is small in the hand, but not in consequence. It can start succession after disturbance, anchor a farming tradition, or alter the balance of a whole region. Few objects so tiny have redirected so much of the living world. A seed is both a beginning and a survival machine. Those two roles work together. We often think of seeds as symbols of fresh starts, but they are also built for hardship in remarkably practical ways. The outer coat can shield the living interior from drying, cold, physical damage, and attack from microbes or hungry animals. Inside, stored food supports the embryo during the dangerous period before roots and leaves can fully take over. Dormancy adds another layer of protection by slowing or suspending activity until conditions improve. In other words, a seed is not just a baby plant. It is a carefully engineered bridge between one generation and the next. That bridge may need to cross winter, wildfire, ocean water, or years of drought. It may need to wait underground while the world above becomes less hostile. Seen that way, the seed is not fragile in the simple sense. It is vulnerable, yes, but also equipped, stubborn, and astonishingly well prepared to keep life moving through uncertainty. Coconuts can cross oceans and still arrive ready to grow. That ability helped coconut palms spread across tropical shores long before ships carried them on purpose. A coconut is more than a seed. It is a traveling vessel built for saltwater journeys. Its fibrous husk traps air, which helps it float, while the tough shell protects the living interior from impact and soaking damage. Inside, the seed carries a rich food supply in the white flesh and liquid that people know as coconut meat and coconut water. That reserve gives the young plant a strong start once it reaches land. Picture one bobbing for weeks or even months through sun, waves, and surf. then washing ashore on a new beach still capable of life. Few seeds are so completely equipped for long-distance dispersal by sea. It feels almost engineered for exploration, as though the palm found a way to send its future drifting across blue water in search of another coastline. Dandelion seeds fly on natural parachutes built from fine hairs. What looks like a simple puffball is actually a remarkably elegant flight system. Each seed hangs beneath a crown of delicate bristles called a pappus, and that little structure changes the air around it in a surprising way. As the seed falls, the hairs create drag and help it descend slowly, which gives even a mild breeze time to carry it away. Researchers have shown that the shape of the pappus can generate a stable vortex above the seed, making the whole design more efficient than its fragile appearance suggests. So when a child blows on a dandelion clock, they are sending dozens of tiny gliders into the atmosphere. Many will land nearby, but some can travel far farther than you might expect. It is a lovely reminder that dispersal does not always require speed or force. Sometimes nature solves the problem with lightness, balance, and a surprisingly sophisticated relationship with moving air. Maple seeds spin like little helicopters to slow their fall. That spinning motion is called auto-rotation, and it turns a simple drop into a controlled descent. Each maple fruit has a wing-shaped extension that catches the air as it falls, causing the seed to whirl. The rotation slows its downward speed and often pushes it sideways too, which helps it land farther from the parent tree. That distance matters. A seedling that sprouts directly beneath a mature maple must compete for light, water, and space in crowded soil. By gliding outward, it improves its odds. The shape is so effective that engineers and biologists have studied these seeds to better understand flight at small scales. Children have played with them for generations, tossing them upward and watching them spin. But the real wonder is that the tree is doing serious physics with a paper-thin structure grown from living tissue. The result is not just charming. It is a practical way of turning air into opportunity. Burdock seeds inspired Velcro by clinging stubbornly to fur. The story began with a walk and a closer look. In the 1940s, Swiss engineer Georges de Mestral noticed burrs sticking to his clothes and his dog's fur after time outdoors. Instead of brushing them off and moving on, he examined them under a microscope. What he saw was a forest of tiny hooks. Those hooks caught onto loops in fabric and hair with impressive reliability, which explained why burdock can hitch a ride so effectively on passing animals. De Mestral used that observation to develop the hook and loop fastener later known as Velcro. It is one of the most famous examples of biomimicry, where human invention follows a design already solved by nature. For the plant, the burr is not a nuisance, but a transport strategy. For us, it became a new, everyday technology. That makes burdock seeds remarkable in two directions at once. They spread themselves, and they also quietly reshaped modern design. Some desert seeds can wait years for a single rainstorm. In a desert, timing is everything, because the wrong beginning can be fatal almost at once. Many annual plants in arid regions produce seeds that remain dormant through long stretches of heat and dryness, sometimes for years, until rain arrives in enough quantity to make growth worth the risk. A brief sprinkle may not be enough. The soil must hold moisture long enough for germination, root growth, and at least a chance of reaching maturity. When the right storm finally comes, the change can be astonishing. Ground that looked empty can burst into green shoots and flowers within days or weeks, as though life had appeared from nowhere. But it was never nowhere. It was waiting underground, held in reserve by patience rather than inactivity. These seeds are part of why deserts can feel so dramatic. Their landscapes are not barren in the absolute sense. They are often loaded with postponed life, listening for rain. Lotus seeds have sprouted after more than 1,000 years. That longevity helped turn the lotus into one of the most astonishing examples of seed endurance ever studied. In one famous case, very old lotus seeds recovered from an ancient lake bed in China were germinated successfully after roughly a millennium. The ages were extraordinary enough to attract broad scientific attention because living tissue had remained viable across spans of time that seem almost unreasonable for a seed. Part of the explanation lies in the remarkable seed coat, which is exceptionally hard and resistant. That barrier helps protect the embryo from moisture changes, microbes, and physical wear. The result is a package that can remain sealed against the world for a breathtakingly long time. There is something almost eerie about seeing a plant from such a distant past resume life in the present. It collapses time. The gap between ancient mud and a modern laboratory suddenly narrows, and a dormant future from long ago begins unfolding again. A seed coat can be hard enough to outlast harsh winters. For many species, that outer layer is the difference between survival and failure. The coat acts as a barrier against cold, drying winds, sudden moisture changes, and the gnawing attention of fungi, insects, and animals. In temperate climates, winter is not just cold. It is unstable. Soil may freeze, fall, refreeze, and stay wet for long periods. A poorly protected embryo would be in constant danger. Hard-coated seeds solve that problem by slowing water entry and shielding the living tissues inside until conditions become more suitable. In some legumes, the coat is so tough that germination may not happen until it is cracked, scratched, or weathered over time. That delay can be useful because it stops the seed from waking during a brief warm spell in the wrong season. So the coat is not mere packaging. It is a gatekeeper. It decides when the outside world has finally become safe enough for the inner life to proceed. Some seeds only open after passing through an animal's body. That journey may sound brutal, yet for certain plants, it is part of the intended route. Fruits tempt animals with sugar, color, or scent, but the real beneficiary is often the tough seed hidden inside. During digestion, the fleshy part is stripped away, while the seed coat may be softened or scarred, just enough to improve germination later. The trip also carries the seed away from the parent plant and leaves it in a fresh patch of ground with a ready-made dose of nutrients. In some habitats, this partnership is so important that the plant's spread depends heavily on the feeding habits of birds or mammals. Without them, seeds may fall in the wrong place or fail to break dormancy as effectively. It is one of nature's more surprising collaborations. An animal eats a meal. A plant secures transport, processing, and delivery. What looks like destruction from one angle becomes successful reproduction from another. Birds hide seeds for later and accidentally plant entire woodlands. Many seed-storing birds behave like small, feathered foresters without ever meaning to. Jays, nutcrackers, and other caching species gather acorns, pine seeds, or nuts and bury them in scattered locations as future food reserves. They rely on memory and landmarks to recover these hidden meals, and they are often impressively good at it. Even so, not every cache is found again. Some are forgotten. Some are abandoned. Some are missed beneath later snowfall or leaf fall. Those neglected stores can germinate, and over time, the results can be enormous. A single bird may bury thousands of seeds in a season, often choosing open ground or disturbed areas that are ideal for establishment. In some mountain and woodland systems, these birds are major partners in the spread of trees. The landscape we admire can partly owe its shape to repeated acts of animal planning, error, and abundance. Forgetfulness, in this case, becomes a force that builds forests. Squirrels forget enough buried nuts to help forests spread. Their reputation for absent-mindedness is a little unfair, because squirrels are often highly skilled at storing food. They scatter berry acorns, hazelnuts, walnuts, and other nuts across wide areas, which protects their winter supplies from theft and local shortage. Many are later recovered through smell and memory. Yet not all of them are found. Some are overlooked because the animal dies, moves away, or simply loses track of a portion of its hidden stores. Those forgotten nuts can germinate in spring, especially when they were buried at a depth that keeps them moist and partly protected. That makes squirrels important seed movers in many temperate woodlands. They do not just consume trees. They help distribute them. In some cases, the burial itself improves the nut's chances by placing it in soil rather than leaving it exposed on the surface. So the squirrel's pantry doubles as a planting system, and tomorrow's woodland can begin as yesterday's missing lunch. Mangrove seeds begin growing while still attached to the tree. In many mangroves, the young plant does not wait for release before it gets started. While still hanging from the parent, the embryo pushes out into a long, narrow structure called a propagule. By the time it drops, it already looks less like a seed and more like a ready-made spear of life. That matters on muddy tropical coasts where timing is harsh and unstable. Tides rise and fall. Salt presses in. Ground can be soft, flooded, or swept clean. A propagule that lands tip first may lodge into the mud quickly and begin establishing before currents carry it away. If it does not stick at once, it can float and travel until it reaches a better place. So the tree sends out offspring with a head start, already partly assembled for a demanding world. It is a striking reminder, but not every seed begins from stillness. Some begin growing before the journey even starts. Some orchid seeds are smaller than grains of dust. At first glance, they barely seem possible as seeds at all. Many orchid seeds are so tiny and light that a single seed capsule can release hundreds of thousands or even millions into the air. They look more like powder than like the sturdy, familiar seeds people imagine when they hear the word. This extreme smallness lets orchids scatter offspring widely on the faintest movement of air, which is useful for plants that often live in patchy habitats on forest floors, tree branches, or remote slopes. But the trade-off is severe. These seeds carry almost no food reserve of their own. They are built for dispersal rather than self-sufficiency. That makes them both daring and vulnerable. A large seed travels with packed supplies. An orchid seed travels almost empty, gambling on scale instead of baggage. It is one of the boldest reproductive strategies in the plant world. Win by being countless, invisible, and everywhere at once. Orchid seeds often need fungi before they can even begin. That dependence makes the orchid story even stranger. Because many orchid seeds are so tiny and carry so little stored food, they cannot simply land and start growing on their own. Instead, they often need help from fungi in the soil or in decaying plant matter. The fungus enters the young seed and provides nutrients that support early development, almost like a life support system during the first stage of growth. Without that partnership, many orchid seeds never make it past the starting line. This means successful germination is not only about moisture, temperature, or light. It can also depend on whether the right microscopic partner is present in the right place at the right time. That helps explain why orchids can be abundant in one patch of habitat and absent in another that looks nearly identical to us. Their future depends on an underground relationship, hidden from view, yet absolutely central to whether their story begins at all. A strawberry wears its true seeds on the outside. What most people call the fruit is actually a swollen, fleshy support structure, while the tiny specks on the surface are the real fruits, each containing a seed inside. Once you notice this, a strawberry becomes one of the most delightfully misleading things in the kitchen. We bite into the red part and think we are eating the fruit in the usual way, but botanically the plant has arranged the whole package differently. Those little outer units are called akens, and each one began from a separate ovary in the flower. The bright red tissue expanded around them later, becoming sweet and attractive to animals that would eat the whole thing and help spread the seeds. So a strawberry is not a simple fruit in the ordinary sense. It is a cluster, a clever assembly, and a reminder that plants often solve familiar problems in unfamiliar ways. Even something as common as a berry can turn out to be a botanical surprise. Sunflower heads can hold thousands of perfectly packed seeds. Stand in front of a mature sunflower, and you are looking at a masterpiece of natural arrangement. What seems like one large flower is actually a crowded community of many small florets, each capable of producing its own seed. As they develop, those seeds are placed in spiraling patterns that often follow mathematical relationships linked to Fibonacci numbers. The result is not decorative by accident. It is an efficient packing system that helps fit a remarkable number of seeds into a circular space without leaving awkward gaps. Each new seed forms at an angle that avoids lining up directly with the last, which helps spread them evenly across the head. This is why the pattern feels so satisfying to the eye. It reflects order emerging from repeated growth. The sunflower is not drawing geometry for beauty alone. It is solving a practical problem of space with extraordinary elegance. In one broad disc, mathematics, reproduction, and visual wonder come together. Pine cones can guard seeds for years before releasing them. That long wait can be crucial in places where the wrong season would doom a seedling almost at once. A cone is not merely a container. It is a protective device built from overlapping scales that can hold developing seeds through cold, drought, wind, and predation. In some species, cones mature and release their contents within a year or two. In others, the scales remain shut for much longer, keeping the seeds protected until environmental conditions become more favorable. During that time, the cone may hang high in the canopy through storms and snowfall, preserving future growth in a suspended state. When the right combination of drying, warming, or aging occurs, the scales begin to open and the seeds can slip free. It is a patient strategy that spreads risk across time. The tree is not throwing all of its chances into one season. It is keeping part of the future in reserve, held above the ground in woody storage. Some cones only open in the heat of wildfire. This is one of the most dramatic examples of plants turning danger into timing. In certain pines and other conifers, the cones are sealed shut with resin so firm that ordinary weather does not release the seeds. The scales remain closed for years, sometimes accumulating in large numbers in the canopy. Then a fire sweeps through. Heat melts the resin, the cones open, and seeds fall onto ground that has been radically transformed. The surface is suddenly clearer. Competing vegetation has been reduced. Nutrients from burned plant matter may be more available. Sunlight reaches places that were once shaded. For species adapted to this cycle, fire is not simply an enemy. It is part of the cue that creates the best possible start for the next generation. There is something astonishing about that logic. A forest burns, and hidden above the flames, unopened cones are waiting for precisely that moment to let the future loose. Acorns feed forests, animals, and entire human cultures. An acorn is not just an oak seed. It is also a major food source that has shaped ecological relationships and human history across wide regions. In woodlands, acorns feed deer, wild boar, bears, mice, jays, insects, and many other creatures. In heavy mast years, oaks can flood the landscape with such abundance that animal populations respond dramatically. That pulse of food can ripple through the whole forest, affecting survival, breeding, and movement. Humans have relied on acorns too. In several cultures, people gathered them in quantity, leached out the bitter tannins, and turned them into flour, breads, porridges, or other staple foods. That takes work, but it turns a hard, overlooked seed into nourishment stored by the tree itself. So the acorn stands at a fascinating intersection of ecology and culture. It grows the next oak, feeds the living world around it, and has also sustained people who learned how to unlock what it carries. The world's largest seed comes from the coco de mer palm. Native to a few islands in the Seychelles, this palm produces a seed so enormous that it can seem almost unreal when seen in person. The coco de mer can weigh many kilograms, making it the undisputed giant of the seed world. Its famous double-lobed shape has drawn fascination for centuries, not only because of its size, but because early sailors sometimes found the seeds floating at sea without knowing where they came from. Before the parent trees were identified, stories grew around them. Some believed they came from mysterious underwater forests. The actual palm is just as remarkable as the myth. It lives only in a narrow natural range, and its reproduction is slow, costly, and tied to a rare island ecosystem. A giant seed like this changes your sense of what a seed can be. It is no dusty speck or wind-blown flake. It is a monumental investment in a single beginning. The world's lightest seeds drift almost like floating specks of air. At the opposite extreme from giant tropical seeds are some of the smallest and least substantial looking in the plant kingdom. Certain orchids produce seeds so light that they seem closer to dust than to anything most people would call a seed. When released, they can rise and move on faint air currents, disappearing almost at once from view. Their lightness is not merely a curiosity. It is a whole strategy. By shedding substantial reserves and minimizing weight, the plant can produce vast numbers and let the atmosphere do the transport. A forest breeze becomes a distribution system. The risk is obvious. Most of these travelers will never land in a place where they can succeed, but the few that do may reach habitats inaccessible to heavier seeds. It is a game of improbable chances played on a massive scale. The smallest seeds are not built to force their way through the world. They are built to vanish into it. Some seeds carry wings, hooks, barbs, or even sticky glue. A seed is often a piece of engineering disguised as a speck of plant matter. Instead of relying on one universal method of travel, plants have evolved an astonishing range of attachments and shapes that match the world around them. Winged seeds can glide or spin. Hooked ones snag passing fur. Barbed seeds grip fabric, feathers, or skin with stubborn determination. Some are coated in sticky substances that cling to anything brushing past. Each design reflects a different solution to the same problem. How do you move when you cannot move yourself? Look closely at a hedgerow, a meadow, or the cuff of a trouser leg after a walk, and you begin to see that plants are constantly reaching outward through these tiny inventions. They are not passive at all. They are manufacturing tools for escape. The seed is not simply falling away from its parent. It is leaving with equipment, shaped by evolution to seize any chance of reaching somewhere new. Tumbleweed spreads seeds by turning the whole plant into transport. This is dispersal on a wonderfully dramatic scale. In certain dry landscapes, the mature plant breaks away from its root once it has dried, and the wind takes the entire body rolling across open ground. As it tumbles, branches knock against stones and soil, and seeds shake loose, little by little, over what can be a surprisingly long journey. Instead of sending each seed out separately, the plant becomes its own vehicle. It is a striking adaptation for places where wide spaces and strong winds offer a natural roadway. The rolling skeleton can cross roads, fences, and fields, scattering future plants as it goes. That is why tumbleweeds carry such a vivid image in popular culture. They are not just symbols of empty country. They are moving seed machines built by arid ecosystems to make use of distance and momentum. What looks like a dead plant wandering aimlessly is actually performing the final act of reproduction. Certain seeds bounce when raindrops strike them with force. Rain does more than water the ground. For some plants, it also acts as a launch mechanism. A falling raindrop carries surprising energy for its size, especially when it hits a smooth or specially shaped fruiting body. In certain species, that impact can jolt seeds out and send them bouncing or splashing away from the parent plant. The distances are not enormous in human terms, but at the scale of a tiny seed, even a short leap can mean escaping crowded roots and dense shade. It is a lovely example of how plants exploit everyday physics. Rain is already arriving. Rather than merely endure it, the plant turns the storm into labor. The seed's movement can look almost playful, yet behind it is a serious advantage. A wet day becomes a dispersal event. The same weather that softens soil and raises moisture for germination also provides the shove that gets the next generation moving across the surface. Some plants fling seeds explosively, like tiny living catapults. This is one of the most startling tricks in the plant world, because it happens with real speed. As the fruit dries or builds internal tension, tissues within the pod twist, tighten, or swell until the structure can no longer hold together. Then, in a flash, it snaps open and hurls the seeds outward. To our eyes, the motion is sudden enough to seem almost animal, yet it is powered entirely by plant tissue storing mechanical energy. Different species solve the problem in different ways, but the result is the same. The next generation is thrown clear of the parent, sometimes surprisingly far. That matters because distance reduces competition for light, water, and nutrients. It also helps the plant colonize nearby gaps in the habitat. What makes explosive dispersal so memorable is the contrast. A plant appears still and silent, then without warning it behaves like a loaded spring. The calm exterior was storing force all along. Touch-me-not pods burst open at the slightest pressure. Few plants make curiosity feel so immediate. In species such as the touch-me-not, the right pod is held under tension, waiting for a disturbance small enough to trigger release. A brush of a finger, a passing animal, or even the movement of surrounding stems can be enough. Then the pod coils back in an instant, peeling apart and flinging its seeds away. It feels almost theatrical, which is why people remember the first time they see it. But beneath that surprise is a serious reproductive strategy. The plant places its seeds into the world with sudden force rather than dropping them straight down into the same crowded patch of ground. That quick movement also takes advantage of contact with animals, who may startle the pod while walking past. In a way, the plant turns interruption into opportunity. Its fruit is a tension-loaded device, quiet until touched, then all action, transforming the gentlest contact into dispersal. Squirting cucumbers launch seeds in a sudden jet of liquid. The name sounds comic, but the mechanism is wonderfully real. In the squirting cucumber, pressure builds inside the ripe fruit as fluids and gases accumulate. When the fruit is disturbed or reaches the right stage of maturity, it detaches from the stalk, and the internal pressure forces the contents out through the opening. Seeds and liquid blast away together in a sudden spray. It is one of the strangest forms of seed dispersal in the plant kingdom, because the fruit behaves almost like a pressurized capsule. This method gives the seeds a forceful departure from the parent plant and can scatter them over a useful distance. It also reminds us that plant movement is often hidden until the final instant. A cucumber relative sitting quietly on a vine does not look like something capable of rapid action. Then it erupts. The effect is bizarre, memorable, and efficient, proving that seeds do not always drift or drop. Sometimes they are fired. Ants collect certain seeds because they come with edible bribes. Some plants have evolved a remarkably clever bargain. Their seeds are equipped with a fleshy, nutrient-rich attachment called an elaeosome, which is especially attractive to ants. To the ant, this little package looks like food worth carrying home. So workers pick up the seed and transport it back to the nest, treating it as a useful prize rather than as plant offspring. Once there, the edible part may be consumed or fed to larvae, while the seed itself is often left intact. The brilliance of the strategy lies in its economy. The plant does not need wings, hooks, or explosive force. It simply offers payment to an animal already excellent at transport. In woodland habitats, this can be a major route of dispersal for spring-flowering plants and other species. The whole exchange feels almost civilized. A tiny food gift is offered. A relocation service is performed, and the plant secures movement through the labor of insects. Those ant-carried seeds often end up planted underground. That destination can be far better than it sounds. After ants bring the seeds back to the nest to harvest the edible coating, the remaining seed is often discarded in chambers, tunnels, or nearby refuse piles beneath the surface. For the plant, that can amount to a remarkably good place to begin. Underground, the seed may be protected from drying sun, surface fires, and some hungry animals. The soil can be loose and nutrient-rich, especially around ant waste deposits, which may give the seedling a stronger start. In effect, the ants are not just moving the seed. They may be delivering it to a sheltered nursery. This is why the relationship is so fascinating. It is not accidental in the broad sense, even if the ants are not consciously gardening. Their normal behavior creates conditions that improve the plant's aunts. A seed that could have lain exposed on leaf litter ends up tucked into the earth by industrious insects. Some seeds sink quickly, while others float for months. That difference can decide the entire geography of a plant's future. In wetlands, rivers, lakes, and coastal zones, buoyancy is not a trivial detail. It is destiny. A heavy or dense seed may drop fast, settling close to the parent, or anchoring in mud before currents sweep it away. That can be useful when the right habitat is already present under the plant itself. Other seeds are built for the opposite strategy. They contain air spaces, fibrous layers, or water-resistant tissues that keep them afloat for long periods. These travelers can drift through river systems or along seashores until they finally meet a bank, beach, or tidal flat suitable for growth. So floating is not always better than sinking, and sinking is not always failure. Each reflects a different answer to the same problem. Stay close to the known habitat or gamble on movement. In watery landscapes, even the simple question of density becomes part of evolution. A seed's shape can decide how far the wind carries it. Wind dispersal is not just about being light. Shape matters enormously. A slight change in wing length, surface texture, or the position of the seed's center of mass can alter how air moves around it, which changes how quickly it falls and how far it may travel sideways. Some seeds spin, some glide, some flutter. Some descend so slowly that even weak turbulence keeps them aloft. This means the architecture of a seed can affect the size of its future range. A well-shaped seed may clear the shadow of the parent plant, reach an open patch of ground, or even cross barriers that heavier, less aerodynamic seeds could never manage. That is why these structures have attracted the attention of physicists and engineers as well as botanists. Each tiny form is a test of flight without muscles. the plant shapes the seed, the air completes the journey, and distance emerges from design. A small contour can change a species' map. Many seeds refuse to sprout until winter has truly passed. For a seed in a cold climate, early warmth can be a trap. A few mild days in late autumn or a brief thaw in midwinter might seem promising, but a seed that begins too soon could be killed by the next freeze. So many species evolved a stricter rule. They remain dormant until they have experienced a long enough stretch of cold to confirm that winter is not merely pausing. This requirement helps synchronize germination with the safer arrival of spring, when daylight is increasing, soil is softening, and the odds of sustained growth are much better. It is a remarkable kind of restraint. The seed does not respond to the first hopeful sign. It waits for proof. That patience shapes entire landscapes. Meadows, woodlands, and fields can stay silent through false starts, then wake together when the season has genuinely turned. What looks like stillness is often a quiet act of judgment beneath the soil. Cold can unlock seeds that would ignore warm weather. That sounds backwards at first. Warmth seems like the obvious invitation to grow, yet for many plants, it is not enough. Some seeds require a period of chilling, often called stratification, before they become capable of germination at all. Until that cold interval has been satisfied, they may sit in perfectly mild conditions and do nothing. This is one of the most elegant seasonal safeguards in the living world. The seed is not asking only whether the present feels comfortable. It is asking whether the recent past confirms the right sequence of seasons. In practical terms, winter acts like a key. It changes internal chemistry, shifts hormone balances, and gradually removes the blocks that kept growth in check. Only then can later warmth have meaning. So the cold months are not wasted time from the seed's perspective. They are part of the activation process itself, a necessary chapter in the script that prepares life to begin. Darkness helps some seeds germinate, while others demand light. That difference tells us something profound about how seeds read the world around them. A seed buried beneath leaf litter or soil is not blind in the simple sense. It can detect whether light is present or absent, and that clue helps determine whether starting now would be wise. Some seeds prefer darkness because it suggests protection, moisture, and a stable position in the ground. Others require light because they are too small to emerge successfully from depth, so they must wait near the surface where a growing shoot has a real chance. This creates a hidden sorting system in the soil. Two seeds may lie only a few centimeters apart, yet one begins while the other remains dormant because each is tuned to a different signal. It is a subtle form of environmental reading. Light is not just energy for future leaves. For many seeds, it is information, a message about place, depth, and survival. Some seeds measure day length before they dare begin. Not all seeds rely on temperature alone. In some species, the length of daylight forms part of the decision about when to germinate or when later stages of development should proceed. Day length is a powerful seasonal signal because it does not swing wildly from one week to the next in the way weather can. A warm spell may mislead. A long enough day rarely does. By responding to photoperiod, a seed or young seedling ties its future to the planet's reliable rhythm rather than to a temporary patch of mild air. This is especially useful in places where springs can be erratic, with warmth arriving early and then vanishing again. The remarkable thing is that a seed buried in soil is connected to the turning year through the faintest environmental cues. It is not counting in any conscious way, yet it is still tracking time with astonishing precision, waiting for a safer stretch of the calendar to open. Fire can crack seed coats and awaken hidden embryos inside. For certain plants, intense heat is not only survivable, it is necessary. Some seeds are sealed inside coats so tough that ordinary weather cannot open them fast enough. Fire changes that. Heat can split, weaken, or alter the outer layer, allowing water to reach the embryo inside for the first time. Until that moment, the seed remains protected and dormant, sometimes for years. Then the coat finally yields, and growth can begin. In habitats shaped by periodic burns, this makes powerful ecological sense. Fire clears old vegetation, opens space, and creates a landscape where competition has suddenly dropped. A seed that wakes into that new setting may have far better odds than one that germinated earlier in crowded shade. The striking part is the transformation of the fire itself. What seems like pure destruction becomes, for these species, a literal unlocking force. The flames do not merely spare the future. In some cases, they help open it. Smoke contains chemicals that tell some seeds the danger is over. This is one of the most astonishing messages in ecology. After a fire, smoke lingers in the air and settles into the ground, carrying compounds that certain seeds can detect. One group of these chemicals, called charikins, has been shown to stimulate germination in various fire-adapted plants. In effect, smoke becomes a signal, but the landscape has changed. The canopy may be opened. Competitors may be reduced. Nutrients may soon be more available. For a dormant seed in the soil, that information is invaluable. It means the moment after destruction may actually be the best moment to begin. What makes this so fascinating is how specific the response can be. The seed is not merely reacting to warmth or moisture. It is responding to a chemical trace of burned vegetation, as if the air itself were delivering news. In that sense, smoke is not just a byproduct of fire. It is part of the conversation between disturbance and renewal. Floodwaters can trigger germination in plants built for wetlands. In many landscapes, flooding looks like chaos from above, but to wetland plants, it can be a seasonal signal rich with opportunity. Some seeds remain dormant until rising water changes oxygen levels, temperature, pressure, or the chemical conditions around them. When those floodwaters arrive, they announce a habitat that is briefly becoming suitable for species adapted to marshes, river margins, and temporary pools. This matters because wetlands are unstable places. Water may spread across a plain, retreat, and return again in cycles that shape everything living there. A seed that germinates too early may dry out. One that waits for inundation is responding to the world that actually sustains it. Floods can also move seeds into fresh silt and newly opened spaces where establishment is easier. So the rising water is not only a threat or a transport system, it is also a cue. For certain plants, the soundless arrival of floodwater is the true beginning of the season. A seed may wait for the chemistry of ash-rich soil. After vegetation burns, the ground is changed in more ways than appearance alone can reveal. Ash can alter soil chemistry, shift nutrient availability, and modify the conditions around dormant seeds. For some species, those changes are part of the cue that the timing is finally right. The soil may become richer in certain minerals. The surface may be more open to light. Competition may have dropped sharply. Together, those signals help create a brief window in which a seedling has a much better chance than it did before the fire. This means the seed is not responding only to flames or smoke. It may also be responding to the transformed earth left behind. There is something extraordinary in that sequence. A plant can wait through years of unsuitable conditions, then detect not just that a fire happened, but that the ground now carries the chemical fingerprint of a new beginning. The ash is not simply residue. It is part of the invitation. Some seeds germinate only after repeated freezing and thawing. A single cold spell, is not always enough. In certain species, the seed responds best after many cycles of freezing and thawing have worked on the coat and surrounding tissues over time. That repeated expansion and contraction can help weaken barriers, alter permeability, and gradually prepare the embryo for water uptake once spring arrives. It is an elegant safeguard against false starts. One short chill does not count. One brief warm patch does not settle the matter either. The seed waits through a whole season of back and forth, using winter's instability itself as evidence that the year is progressing normally. This is especially useful in climates where snow cover comes and goes, or where the soil repeatedly shifts between frozen and softened states. To us, that pattern can feel harsh and exhausting. To the seed, it is information. Each freeze and thaw is another mark in a long sequence, and only when enough marks have accumulated does the lock finally loosen. Others need abrasion, pressure, or stomach acid to wake. Some seeds are designed to begin only after being roughed up. Their coats are so resistant that ordinary moisture cannot get inside until something physically alters the surface. That change may come from grit grinding them in soil, trampling pressure from animals, passage through a digestive system, or the corrosive action of stomach acid. In each case, the outer barrier is scarred or softened, just enough to let water in and germination begin. It is a wonderfully practical strategy. The seed avoids sprouting too soon, but it also ties its awakening to meaningful events. A seed that survives digestion has likely been carried to a new place. One that is worn by soil movement or pressure may be in active ground where establishment is possible. So the rough treatment is not accidental damage in evolutionary terms. It is part of the plan. For some species, life begins not after comfort, but after a measured encounter with force. Inside a seed, the first root already knows where down is. Before a seedling has seen the sun, before it has unfolded a leaf, its first act is usually to send a root into darkness. That direction is not random. The embryonic root responds to gravity, which gives the young plant an immediate sense of orientation at the very moment life resumes. Even if a seed lands upside down, the root can curve and correct itself, pushing into soil where water and minerals wait. That is one of the marvels hidden inside germination. The plant begins with direction before it begins with vision. It does not need to guess where stability lies. It already has a system for choosing. This matters because the first root is not merely an anchor. It is the seedling's lifeline, the structure that must secure moisture before the stored reserves run low. So one of the earliest decisions in a plant's life is also one of the most intelligent sounding. It starts by finding down. The first leaves inside a seed are packed in miniature. A seed is not waiting to invent a plant from scratch after it wakes. In many species, the embryo already contains tiny folded structures that will become the first visible parts of the seedling. Under magnification, those early leaves can look astonishingly complete, tucked into a space so small that the whole arrangement feels almost impossible. They are held in readiness, compressed by the architecture of the seed, then expanded when water returns and growth begins. This makes germination feel less like a sudden creation and more like a careful release. The form was already there, hidden and compact, waiting for room and moisture to unfold. That idea changes the way you look at an ordinary seed. It is not a blank point of possibility. It is a plant in a tightly folded state, already carrying the outlines of what comes next. The first glimpse of green was not improvised at the surface. It was prepared in silence beforehand. A seed embryo can pause life without quite becoming dead. That strange middle state is one of biology's most extraordinary balancing acts. In dormancy, the embryo is not growing in any visible way, yet it is not lifeless either. Its activity is reduced to a whisper, its metabolism slowed so dramatically that time seems almost suspended. This allows the seed to endure conditions that would kill an actively growing plant, including long dry periods, cold storage, and months or years of waiting underground. It is survival through restraint. The embryo does not fight the hostile world head-on. It lowers itself beneath the threshold of urgency and remains there until circumstances improve. That is why a dry seed can feel deceptively inert in the hand. It seems still, but its stillness is strategic rather than empty. Somewhere inside, the line between life and waiting is being held with astonishing precision. The future plant is neither gone nor fully present. It is paused, preserved, and listening for the moment to resume. Seeds store oils, starches, or proteins for the journey ahead. That stored food is the seedling's first inheritance, set aside before it ever enters the world. Different plants invest in different reserves. Some pack energy-rich oils, which are dense and powerful fuel. Others rely more heavily on starch, a carbohydrate store that can be broken down as growth begins. Still others contain significant proteins, which help supply the raw materials needed for building new tissues. This reserve matters because a germinating seedling cannot immediately live on sunlight alone. Before leaves are fully active and roots are properly exploring the soil, it needs internal support. So the seed sets out carrying provisions, a biological travel ration prepared by the parent plant in advance. Even many foods people prize, from sunflower seeds to beans and sesame, are delicious partly because they are nutrient stores meant for new life. That gives seeds a certain drama at the table as well as in the field. We are often eating concentrated beginnings. The endosperm is a lunchbox packed before the plant is born. Inside many seeds lies a tissue whose job is simple and vital. It is there to feed the embryo. That tissue, called endosperm, forms during seed development and becomes a stored food source that can support early growth once germination begins. In grains such as wheat, rice, and maize, it makes up much of what humans mill and eat, which means entire civilizations have depended on plant baby food without thinking of it that way. For the seedling, this reserve is a bridge between dormancy and independence. It supplies energy before roots are fully established, and before leaves can capture enough light to keep the whole system running. There is something wonderfully practical about it. The parent plant does not simply create an embryo and send it away. It packs a meal with it. That small act of provisioning sits at the heart of agriculture, ecology, and everyday life, hidden inside some of the most familiar foods on Earth. Cotyledons can feed the seedling before true leaves appear. These first seed leaves are among the plant world's most overlooked actors. In many species, cotyledons emerge early and provide stored nourishment, or begin photosynthesis before the later, more familiar adult leaves take over. They often look simpler than the leaves that follow, sometimes broader, thicker, or oddly shaped compared with the mature plant. That is because they are not built for the long career ahead. They are built for the emergency of arrival. Their task is to help the seedling survive the vulnerable stretch between awakening and stability. In beans, for example, the cotyledons can rise above the soil and briefly become the dominant visible structures, thick with reserves from the seed itself. In other plants, they remain below ground and hand over nutrients from there. Either way, they are the opening crew of the plant's life, stepping on stage first so the rest of the body has time to assemble. They are temporary, but they are crucial. Some seedlings emerge wearing the seed coat like a helmet. It can look almost comical at first, as though the young plant has pushed upward still dressed in part of its former life. In certain species, The seed coat remains lodged over the first leaves or shoot tip as the seedling rises through the soil. This can happen because the coat is tight, the soil offers little resistance, or the emerging tissues have not yet shed it completely. The result is a tiny green stem carrying a dark cap, sometimes for only a short time, sometimes long enough to be easily noticed in a garden tray or field. Yet the image is more than charming. That lingering coat can briefly protect delicate tissues as they force their way upward into a world of drying air and direct light. It is a visible reminder that germination is not a clean switch from seed to plant. The old form and the new one overlap. For a moment, the past is still clinging to the future. Germination begins with water, but timing decides survival. Water is the trigger that reawakens the seed. It soaks into dry tissues, swells cells, activates enzymes, and restarts the chemistry of growth. Without it, the embryo remains in suspension. But the arrival of water alone is not enough to guarantee success. A seed can absorb moisture and begin beautifully, only to fail if the season is wrong. The soil soon dries, or the young plant encounters heat, cold, shade, or competition it cannot yet handle. That is why the first sip is only half the story. Germination is not merely a biological event. It is a gamble placed against the calendar and the local environment. The seed must begin when moisture is likely to last, when temperatures are suitable, and when the next steps are possible. A perfect internal mechanism can still lose against bad timing. That tension makes the moment of germination feel thrilling. Life has restarted, yes, but now the world must cooperate long enough for that decision to pay off. One wrong frost can destroy a seedling after perfect germination. This is the cruel side of beginning. A seed can receive water at the right moment, send out its root, lift its shoot, and do everything correctly, only for a sudden return of cold to end the story in a single night. Young seedlings are especially vulnerable because their tissues are tender, water-rich, and not yet well defended against freezing. Ice can rupture cells, blacken leaves, and halt growth before the plant has built any real resilience. That is why spring can be such a dangerous season. It offers possibility, but it also carries hidden knives. A warm spell tempts the seedling into motion, and then a late frost tests whether that choice came too soon. Entire fields and gardens can bear the mark of that mistake. This is part of what makes seed timing so consequential. Germination is not victory. It is exposure. The seedling has stepped out of safety, and the weather now gets its chance to answer. A seed's first days are often the most dangerous. The drama of a plant's life is easy to notice when it becomes tall, leafy, or productive, but the most perilous chapter often comes right at the start. In those first days, the seedling is small, soft, and dependent on a narrow margin of good fortune. It can dry out quickly. It can be uprooted by rain, buried by crusted soil, snapped by a careless footstep, eaten by an insect, or shaded by stronger neighbors before it has fully established itself. Its root system is tiny. Its energy reserves are limited. Its first leaves are just beginning the work of independence. This means the world does not need to be spectacularly hostile to end the attempt. Ordinary hazards are enough. That is why so many seeds are produced in the first place. A plant often solves early fragility not by making each seedling invincible, but by making many and letting chance, timing, and adaptation determine which ones endure. Survival begins as a numbers game. Seed banks protect palm futures in freezers, vaults, and fields. A seed bank is one of humanity's most far-sighted inventions. Instead of waiting for a crop to vanish or a wild plant to slip into decline, people collect seeds in advance and store them under carefully controlled conditions, often cold and dry, so they remain alive for years or decades. Some collections sit in scientific institutions. Some are kept in national facilities. Some live on in living field collections, where plants must be grown and renewed, generation after generation. Together, they form a kind of botanical backup system for the planet. If disease, war, climate shifts, or simple neglect wipe out a variety in one place, saved seeds may help restore what was lost. There is something deeply moving in that effort. It means people looked to the fragile future and decided not to trust memory alone. They chose to preserve possibility in physical form, one labeled packet at a time, before absence had the chance to become permanent. The Svalbard vault stores backup seeds from around the world. High in the Arctic, deep inside a mountain on the Norwegian archipelago of Svalbard, there is a place built to protect the future of food crops. The Global Seed Vault was designed as a backup for other seed collections, a secure reserve where duplicates can be stored in cold, stable conditions, far from many of the dangers that threaten agriculture elsewhere. Its location matters. Permafrost, remoteness, and thick rock all add layers of protection. Inside, shelves hold packets sent by seed banks from many countries, each containing varieties that might one day be needed again. The vault does not replace farmers, fields, or ordinary conservation work. It stands behind them, quietly holding insurance against catastrophe. That idea is what makes it so gripping. In an age often obsessed with speed, this place is devoted to continuity. It is a chamber of stored resilience, where the future of bread, rice, beans, and harvests waits in silence under snow and stone. Saving seeds can preserve foods that might otherwise disappear forever. Not every loss in agriculture is dramatic enough to make headlines. Sometimes a local bean, melon, wheat, or tomato simply slips out of use when a few commercial varieties take over the market. A farmer retires. A village changes its habits. A seed line that carried unusual flavor, drought tolerance, or regional history is no longer replanted. Once that chain breaks, recovery can be impossible unless someone saved seed in time. That is why seed saving matters so much. It preserves not just biological material, but tastes, traditions, and options for the future. A forgotten variety may carry resistance to a disease that later becomes important. It may thrive in a climate that is becoming more common. It may simply taste better than the uniform alternatives that replaced it. Every saved seed packet can hold an edible memory of a place and a people. Without such efforts, whole food stories can vanish without ever being formally recorded. Ancient farming rose when people learned to store and replant seeds. That shift was one of the great turning points in human history. For countless generations, people gathered wild plants from landscapes they moved through. Then, in several parts of the world, humans began saving selected seeds from useful plants and sowing them again in chosen places. That changed everything. Storage meant food could outlast the season of harvest. Replanting meant people could influence which plants became more common near home. Over time, this encouraged settlement, planning, and a closer relationship with the rhythm of land and weather. Villages grew where repeated sowing and harvesting made long-term life more practical. Fields replaced some of the uncertainty of foraging with a different kind of uncertainty, one tied to cultivation, labor, and yield. The remarkable part is how much of civilization rests on that humble act of holding seed back instead of eating it. A future city can begin with someone deciding that not every grain belongs to today. Wheat, rice, and maize seeds helped build whole civilizations. These seeds are not merely crops. They are foundations. Wheat supported expanding societies across parts of the ancient Near East, Europe, and beyond. Rice shaped landscapes, labor, and culture across much of Asia through paddy fields, irrigation systems, and astonishing human effort. Maize became central to civilizations in the Americas, feeding cities, ceremonies, and complex agricultural worlds. Each seed could be dried, stored, transported, planted at scale, and transformed into staple foods that sustained large populations. That reliability gave rulers, traders, farmers, and empires something to build upon. Roads, taxation, seasonal calendars, granaries, and social hierarchies all grew in part from the management of seeded harvests. When we look at old monuments and great urban centers, it is easy to focus on stone and power. But behind them stood fields. Behind the fields stood seeds. A kingdom's endurance could depend less on its walls than on whether the next sowing and harvest would succeed. Coffee, cocoa, and peanuts all begin as seeds we consume. Some of the world's most beloved flavors come from eating seeds, though we do not always think of them that way. Coffee beans are the processed seeds inside the fruit of the coffee plant. Cocoa beans are the fermented and roasted seeds of cacao, the source of chocolate. Peanuts are seeds too, though they take a stranger path than most, developing in pods underground after the flower's stalk bends down into the soil. That means morning alertness, sweet comfort, and salty snacks all trace back to the same fundamental plant strategy: packing nourishment into the next generation. What humans did was intervene in the journey. We learned to roast, grind, ferment, crush, and transform these seeds into entirely new sensory experiences. The result is almost magical. Something meant to feed an embryo becomes a drink, a dessert, or a staple food woven into daily life and global trade. Many of our strongest cravings begin as plant futures repurposed. Many spices are seeds, including cumin, mustard, and coriander. That fact makes the spice rack feel more alive. These tiny flavor bombs are not random plant fragments. They are reproductive structures filled with chemistry that evolved for reasons beyond pleasing human tongues. Cumin seeds carry warm, earthy depth. Coriander seeds offer citrusy brightness. Mustard seeds contain compounds that become pungent when crushed and mixed with moisture. Each seed stores oils and defensive chemicals that can deter predators, resist damage, or shape its interactions with the world. Humans discovered that these same compounds create astonishing flavor. So kitchens became places where reproduction meets culture in a surprisingly intimate way. Every pinch of spice is a small act of botanical transformation. A seed built to protect and continue a species becomes seasoning for bread, curry, pickles, or stew. There is something delightful in that reversal. The next generation of a plant ends up flavoring ours, changing entire cuisines with structures small enough to spill from a spoon. Sesame seeds helped flavor kitchens long before written recipes. Long before cookbooks fixed ingredients on a page, sesame was already part of human food traditions across wide regions of the world. It is one of the oldest oilseed crops known, valued not only for its nutty taste but for the rich oil locked inside its tiny seeds. That oil keeps well, carries flavor beautifully, and made sesame useful both as food and as a practical agricultural resource in hot climates. The seeds themselves could be scattered onto breads, ground into pastes, or pressed for oil that entered cooking in many forms. Because sesame traveled through trade and cultivation so widely, it slipped into different culinary worlds with remarkable ease. It appears in ancient agricultural histories, religious settings, and everyday meals, linking domestic life to very long human timelines. There is something lovely about that continuity. A tiny seed still sprinkled over modern food was already seasoning human experience in eras so distant, but the recipes were carried only by memory and voice. Nutmeg is a seed hidden inside a bright tropical fruit. The spice on a winter dessert begins in a far more vivid setting than many people imagine. Nutmeg comes from the seed of a tropical tree whose fruit splits open when ripe to reveal a dark central seed wrapped in a bright red lacy covering. That red covering is mace, another spice entirely. So one fruit yields two famous seasonings, layered one around the other, like a botanical treasure chest. For centuries, this made nutmeg enormously valuable. It was desired not only for flavor but for status, trade, and medicine, and its scarcity once helped drive global competition and colonial violence. The seed itself travels from tropical heat into kitchens far away, where it is grated into sweet dishes, savory sauces, and festive drinks. That contrast is part of its fascination. Behind the familiar warm scent lies a bright fruit on an evergreen tree and a long history of ships, ambition, and botanical wonder, all centered on a single seed. What we call grains are really carefully harvested seeds. That simple truth reshapes breakfast, bread, and entire farming landscapes. Wheat, oats, barley, rice, millet, rye, and maize are all grasses, and the parts we harvest and eat are their seeds. Each one is a compact package built to produce another plant. Yet humans learned to collect them in immense quantities, dry them, store them, grind them, and turn them into flour, porridge, noodles, breads, and countless other foods. This works so well because grass seeds are durable, energy-rich, and produced in abundance. Their success in nature became their success in agriculture. Over time, humans selected forms that held onto seeds longer, grew more uniformly, or yielded more heavily, turning wild grasses into staples that feed billions. So a field of grain is not merely a field of food. It is a landscape of futures harvested before they can germinate. Civilization has long depended on interrupting that next step and eating the beginning instead. A seed can carry the genetic memory of countless generations. Inside a seed lies more than the plan for one plant. It also carries a long inheritance shaped by weather, disease, soil, competition, and chance across many generations before it. The seed does not remember in a human way, yet its genes hold the results of old struggles. If ancestors survived drought, pests, salt, or cold, traces of that history may still influence what the next plant can endure. In that sense, each seed is a time capsule written in living code. It arrives in the present carrying outcomes from a past no eye can see directly. That is one reason seeds matter so much to evolution. They are not only beginnings, they are continuity made portable. Hold one in your palm, and you are holding a present moment shaped by ancient selection. The future plant has never met its distant ancestors, but it still bears the marks of everything that helped them survive long enough to reproduce. Selective breeding changed wild seeds into the crops we know. The seeds that fill modern fields are often the result of thousands of years of human choice. Early farmers noticed differences among plants. Some had larger seeds. Some tasted better. Some were easier to harvest, store, or grind. By saving seed from those preferred plants and sowing it again, generation after generation, people slowly reshaped entire species. This was evolution guided by human attention. The changes could be dramatic, though they arrived gradually. Seeds became bigger, softer, less bitter, more uniform, or less likely to scatter before harvest. Plants that once lived by their own wild logic were drawn into partnership with people and changed by that relationship. What makes this so remarkable is that it did not begin in laboratories. It began in fields, villages, and ordinary hands choosing what to keep. Much of the modern food world grew from repeated acts of noticing. Human preference became a force that altered the future of seeds. Corn was transformed from a grass with tiny, hard kernels. Modern maize feels so abundant and familiar that it is easy to forget how extraordinary its history is. Its wild ancestor, teosinte, looks so different that the relationship can seem almost unbelievable at first sight. Teosinte bears small, hard-encased kernels in far fewer numbers, arranged on slender structures rather than on the thick ears people know today. Yet through long human selection in ancient Mesoamerica, that modest grass was gradually turned into one of the world's most productive crops. People chose plants with traits they valued, then planted those seeds again and again across generations. Over time, the ears grew larger, the kernels became more exposed and usable, and the plant itself changed into something far more dependent on cultivation. This transformation is one of the clearest demonstrations of what seed selection can do. A wild grass was not merely improved. It was remade into a crop that now feeds vast populations across the planet. Seedless fruits still depend on seeded ancestors somewhere in their history. A seedless grape or banana can feel like a triumph of convenience, but behind that convenience lies a lineage that began with ordinary seeded plants. Seedlessness does not appear from nowhere. It arises through mutations, breeding, or human cultivation of forms that produce little or no mature seed, while the deeper ancestry still traces back through countless seeded generations. In many cases, people maintain these plants not by sowing seed, but by cloning them through cuttings, grafts, or offshoots. That means the familiar fruit in a shop may come from a plant line that survives only because humans keep propagating it. The irony is beautiful. We praise the absence of seeds in what we eat, yet the entire possibility depends on plants whose past was full of them. Even when seeds disappear from the fruit bowl, they remain present in the story. The seedless present still rests on a seeded evolutionary past that made it possible. Plant breeders sometimes chase bigger seeds, sweeter seeds, or tougher seeds. Breeding is often a pursuit of trade-offs disguised as improvement. A breeder may want larger seeds for yield, sweeter seeds for taste, thicker coats for storage, or stronger tolerance to heat, drought, or disease. Yet pushing one trait can influence others in ways that are not always obvious at first. A seed that is larger may demand more from the plant. A sweeter variety may become more vulnerable to pests. A tougher coat may help storage while making germination slower. So breeding is not simply about creating the best seed in the abstract. It is about deciding which qualities matter most for a particular field, climate, market, or use. This is what makes it such a fascinating human craft. Every seed line reflects priorities. Someone chose what kind of future to emphasize. Behind the harvest lies a series of decisions about flavor, resilience, size, labor, and risk, all condensed into the traits carried forward. Wild seeds often survive better, even when crops produce more. Crop plants are champions of productivity under favorable conditions, but wild relatives often excel at something just as important: survival under stress. In natural habitats, seeds face drought, poor soil, irregular seasons, pests, grazing, and competition without human help. Over long spans of time, that pressure can produce seeds with remarkable toughness, dormancy control, or flexibility in harsh environments. Crops, by contrast, are often bred to perform in managed fields where irrigation, fertilizer, and protection reduce some of those pressures. That can make them wonderfully productive, yet less resilient outside those carefully supported conditions. This is why wild seedlines matter so much to science and agriculture. They may hold traits that become invaluable when climates shift or new diseases spread. The future of farming may depend in part on plants that still remember how to cope without our assistance. Abundance is impressive, but endurance is a different gift, and the wild often guards it better. Some invasive plants spread because their seeds travel too well. A plant becomes especially troublesome when its seeds are not only fertile, but highly mobile and difficult to contain. Some invasive species produce huge numbers of seeds that cling to vehicles, float along waterways, survive disturbed ground, or hitch rides in agricultural material. Once they reach a new habitat, rapid dispersal can help them outrun local control efforts. Roadsides, riverbanks, construction sites, and grazed land become stepping stones. A plant that might have remained modest in its native range can suddenly behave very differently when introduced elsewhere, especially if predators, diseases, or competitors that once kept it in check are absent. The real menace is often not just growth, but spread. One season's small patch becomes next year's wide front. Seeds are the engine of that advance. They turn an introduction into an expansion. When people talk about invasive plants taking over a landscape, it is often the seed's talent for movement that makes the takeover possible. Tiny hitchhiking seeds have crossed continents in mud on boots. The journey does not need to be grand to be world-changing. A seed caught in a bit of wet soil on the boot sole, a tire tread, or the hoof of an animal can travel astonishing distances compared with what the plant could ever achieve alone. Trails, farms, ports, rail lines, and hiking routes become accidental corridors for botanical movement. What makes this so striking is the scale mismatch. A person may think they're carrying nothing at all, yet hidden in a smear of mud could be the future of a species in a completely new place. Some seeds are small enough to vanish into the dirt while remaining fully capable of germination later. This is one reason biosecurity rules can seem so strict about cleaning footwear and equipment. The risk is real. The world's floras have been quietly mixed, in part, by invisible passengers traveling where people go, one unnoticed clump of mud at a time. Ship ballast, animal feed, and trade once moved seeds worldwide. Long before modern biosecurity, the ordinary machinery of commerce was already reshaping plant geography. Ships carried ballast to stabilize their loads, and when that ballast included soil, sand, or stone from distant places, seeds often came with it. When the ballast was later dumped in a new port, foreign plants gained an unexpected arrival point. Animal feed did something similar. Fodder gathered in one region could contain seeds that survived transport and later escaped where livestock were kept. Trade in wool, grain, timber, and raw materials also carried seeds across borders without anyone intending it. These were not rare accidents. They were built into the movement of goods and empires. A harbor, market town, or rail depot could become a botanical crossroads. That is part of what makes global plant history so fascinating. Exploration and commerce did not move only people and products. They also moved silent beginnings, tucked into the infrastructure of trade. A single contaminated seed lot can reshape an ecosystem. When crop seed is harvested, processed, and distributed, there is always a risk that unwanted seeds may be mixed in. Sometimes that contamination is minor. Sometimes it is transformative. If a batch contains the seeds of a vigorous weed or an invasive species, sowing it across farms or restoration sites can release that plant into new habitats all at once. Instead of one accidental arrival, many fields become starting points. From there, the spread can be fast, especially if the contaminant resembles the crop at an early stage. or persists in the soil for years. The consequences ripple outward. Farmers may face new control costs. Native plants may be displaced. Pollinators, grazing patterns, and water use can all shift as the introduced species establishes itself. It is a reminder that ecosystems can be altered not only by dramatic disasters, but by mistakes hidden in ordinary commerce. One compromised bag can become the beginning of a much larger story. Some seeds carry natural chemicals that stop nearby rivals sprouting. Not every seed enters the world ready to share. Some are wrapped in chemical defenses that can leak into the surrounding soil and make life harder for nearby competitors. These substances may slow germination, reduce early growth, or create a brief zone of advantage around the seed or the seedling that follows. It is a subtle form of botanical aggression. Instead of fighting after both plants have emerged, the future plant tries to tilt the contest before it even begins. In crowded habitats, that edge can matter enormously. Light, water, and root space are limited prizes, and the first days of establishment are often decisive. So a seed may arrive not only with food and instructions, but with chemistry that shapes the neighborhood. The effect is invisible to us, yet powerful at plant scale. Beneath the soil, a quiet negotiation is taking place, and some seeds begin the conversation by making it harder for others to answer. Others wait until competing plants are gone before beginning. In many habitats, the safest moment to germinate is not whenever moisture arrives, but when the crowd has thinned. Some seeds remain dormant until shade has lifted, leaf litter has been disturbed, grazing has opened gaps, or older plants have died back enough to leave room. They are not simply waiting for comfort. They are waiting for opportunity. A densely occupied patch of ground can be a terrible place for a new seedling. Roots are already established. Light is stolen overhead. Water disappears fast. A seed that starts in those conditions may lose before it has properly begun. But when a tree falls, a bank erodes, a field is turned, or a seasonal canopy collapses, the balance changes. Space appears. Sun reaches the soil. The seed reads that opening and acts. What seems like patience is really strategic timing. The plant is not afraid to begin. It is refusing to begin in someone else's shadow. Desert annuals hedge their bets by not sprouting all at once. This is one of the cleverest survival strategies in harsh environments. After rain, it might seem logical for every seed in the soil to wake together and seize the rare gift of moisture. But for desert annuals, that would be dangerously reckless. If all the seeds germinated in one promising season and the weather then turned bad, an entire generation could vanish at once. So many species spread the risk. Some seeds respond to the first good conditions, while others remain dormant in reserve, sometimes for several more years. The result is a layered future hidden in the ground. Even when the desert blooms spectacularly, not every possible plant has joined the performance. Some are still waiting below, untouched by the apparent signal to begin. That restraint makes the burst of desert flowers even more astonishing. What looks like sudden abundance is actually only part of the stored potential, released in measured portions against an unpredictable world. That strategy keeps one bad season from wiping them out. Nature often survives not by certainty, but by refusing to gamble everything on one throw. When a seed population spreads germination across multiple seasons, it creates protection against disaster. A single dry spell, heat wave, grazing event, or failed rainfall pattern can destroy the seedlings that started too soon. Yet the species itself remains safe because many seeds never join that attempt. They stay hidden in the soil, intact and ready for later chances. This matters especially in places where good years and bad years are sharply separated. and where appearances can be dangerously misleading. One promising storm does not guarantee a full season of growth. One early flush of green can still end in failure. By dividing the future, the plant reduces the risk of total loss. It is a brilliant answer to uncertainty. The species endures because it refuses to act as though the world will be generous every time. Caution becomes continuity. Certain seeds can survive intense dryness by entering deep dormancy. For these seeds, drought is not simply an obstacle. It is the condition they are built to outlast. When water disappears, their internal activity can sink to an extraordinarily low level, allowing the embryo to remain viable through months or years that would kill an active plant outright. The tissues are stabilized, the metabolism is reduced, and the future is held in suspension until moisture returns. This is more than ordinary waiting. It is a profound physiological retreat from danger. In deserts, dry grasslands, and seasonally harsh climates, that ability can mean the difference between a vanished generation and a postponed one. The astonishing part is how complete the pause can feel. A seed in deep dormancy may seem utterly lifeless, yet the next rainfall can reveal that it was never gone at all. It was enduring in the only way possible, by stepping almost completely outside the tempo of growth and holding itself there until the world softened again. Resurrection plants begin from seeds built for impossible-seeming drought. The adult plants earn their dramatic name because they can survive severe drying and revive when water returns. But that story starts earlier, in seeds prepared for landscapes where moisture is rare, brief, and unreliable. In such places, every stage of life must be tuned to scarcity. The seed cannot assume a mild beginning or a steady supply of water. It must endure long exposure, then respond with speed when the moment finally arrives. That means tough protection, careful dormancy control, and an embryo ready to act fast once conditions allow. The future plant is being launched into one of the harshest environments on Earth, and the seed carries the first version of that resilience. There is something deeply impressive about such beginnings. Before the plant ever becomes famous for reviving after desiccation, its seed has already solved the first impossible problem. It has learned how to wait through a world that withholds almost everything, then begin anyway. Arctic plants race from seed to flower in a brief summer. Far north, the growing season can be astonishingly short. Snow retreats, the ground softens, and for a narrow window, the light returns in abundance. Arctic plants must use that interval with extraordinary urgency. A seed that germinates there is entering a race against time, cold, and the rapid return of winter. Some species move from emergence to flowering and seed production with remarkable speed, compressing what would take much longer in milder climates. This does not mean the process is easy. The soil may still be shallowly thawed, winds can be fierce, and temperatures can swing abruptly. Yet these plants are adapted to make use of every available day. In such places, delay can be fatal. The next generation must be set before the season closes again. That gives Arctic plant life a special intensity. The landscape may appear sparse, but beneath that sparseness is a fierce timetable, and seeds are the first to answer it. Alpine seeds face wind, cold, and soil that barely exists. High in the mountains, the ground itself can seem uncertain. Soil is often thin, rocky, unstable, and interrupted by frost, scree, and steep slopes. A seed landing there is not arriving in a generous garden bed. It is arriving in fragments of opportunity. Wind may strip moisture away. Cold can return, even in summer. Meltwater may vanish quickly through stony ground. In such settings, successful seeds must be exquisitely matched to hardship. Some settle into cracks where a little shelter collects. Some wait for brief warm periods close to the ground. Some produce compact seedlings adapted to stay low and avoid the worst exposure. The remarkable thing is not just that alpine plants exist, but that their seeds can begin at all in terrain so physically unforgiving. Each successful sprout feels like a defiance of altitude. The mountain offers almost nothing freely, yet seeds still find ledges of possibility and turn them into living footholds. Rainforest seeds may die quickly if they dry out. Not all seeds are designed for long waiting. In humid tropical forests, some are built for immediate opportunity rather than prolonged endurance. These seeds, sometimes called recalcitrant, are rich in water and highly vulnerable to drying. If they lose too much moisture, they may die outright instead of entering safe dormancy. That creates a very different rhythm from the one we often imagine. The seed falls and the clock is already ticking. In the rainforest, that strategy can work because warmth and moisture are often available, and the environment rewards rapid establishment more than long-term storage. But it also means these seeds are difficult to preserve in conventional seed banks, since the drying methods that protect many other species can destroy them. There is something striking about that fragility. A seed can be perfectly suited to one world and astonishingly vulnerable outside it. Rainforest life often depends not on waiting longer, but on beginning before the moisture is lost. Not all seeds are built to wait a long time. It is tempting to think of seeds as nature's universal patience machines, but that is only part of the story. Many can endure long dormancy, yet others are designed for speed. They are released into seasons or habitats where hesitation would be wasteful or dangerous, and their best chance lies in starting almost at once. Fresh moisture, open ground, and warm temperatures may create a narrow opportunity that will not last. In those cases, a seed built for long delay could miss the moment entirely. So evolution has produced many different kinds of future. Some are cautious and long-lived. Some are urgent and short-tempered. Both strategies can be brilliant when matched to the right environment. That is part of what makes seeds so endlessly fascinating. There is no single seed solution. Each one reflects a habitat, a risk, and a different wager on time. Even at the very beginning, plants are solving the world in multiple ways. Some plants make fake seeds, but real ones still do the work. Nature sometimes produces lookalikes. In certain plants, structures that resemble seeds can form without following the usual route of sexual reproduction. Some are really dry fruits being mistaken for seeds. Others are special reproductive bodies made in unusual ways, giving the appearance of a seed without the full story we normally expect. Yet even in those strange cases, the essential work remains the same. The plant still needs a durable package that can travel, survive, and begin again. That is what gives true seeds their lasting importance. They combine protection, stored resources, and a living embryo in one remarkably effective design. So when botanists sort real seeds from imposters and near equivalents, they are not being fussy for the sake of it. They are distinguishing one of evolution's great inventions from everything that only resembles it. The copies can be clever, but the original design changed the history of life on land. Ferns spread by spores, which are not seeds at all. That difference matters because spores and seeds solve the future in very different ways. A fern releases tiny single-celled units that carry no embryo, no packed food supply, and no protective seed coat. Each spore is more like a minimal starting point than a prepared young plant. When it lands in the right damp place, it grows into a small, delicate stage that must then produce sex cells before a new fern can arise. So the life cycle is longer, stranger, and much more exposed than the seed-based system that flowering plants and conifers use. This is why ferns often thrive in moist habitats, where that vulnerable stage has a real chance. Their method is ancient, elegant, and still successful. But it belongs to a different chapter in plant evolution. Seeing their contrast makes seeds seem even more remarkable. They are not the only route into the future, but they are a very different kind of answer. Mosses conquered land without seeds long before flowering plants appeared. That achievement is easy to overlook because mosses seem so small and humble today. Yet their ancestors were part of a profound transition, helping plant life establish itself on land long before the rise of flowers and fruits. They did it without seeds, without wood, and without the elaborate vascular systems that later plants would develop. Instead, they relied on spores and on a life cycle closely tied to moisture, especially for reproduction. This made them more dependent on damp conditions, but it did not stop them from spreading across rocks, soil, bark, and bare surfaces where they could hold on. In some of Earth's earlier landscapes, plants like these were among the pioneers. They softened ground, trapped moisture, and began the slow work of making land more hospitable to other life. So when you see moss on a wall or stone, you are looking at a lineage that helped begin the greening of the continents without ever needing a seed. Seeds changed evolution by freeing plants from constant water for reproduction. Earlier land plants were often tied to wet conditions because their reproductive cells needed water to meet and complete the process. Seeds helped break that constraint. With the rise of pollen and seed-based reproduction, plants gained a way to reproduce without depending so directly on films of surface water at the crucial moment. That was revolutionary. It meant reproduction could succeed in drier places and under more varied conditions than before. The seed then took the result of that process and wrapped it in protection, turning the next generation into a portable, resilient package rather than a fragile, immediate outcome. This did not make plants independent of water in every sense, of course. Growth still needed it, but reproduction was no longer chained so tightly to constant wetness. That shift opened vast new possibilities across the land. Evolution did not just invent a better package. It changed the places where plant life could afford to dream of becoming permanent. The rise of seeds helped plants colonize harsher, drier worlds. Once plants could protect embryos, store resources, and postpone growth until conditions improved, the map of possibility widened dramatically. Dry slopes, seasonal climates, open interiors, and more unpredictable landscapes became far easier to occupy than they had been for many earlier plant lineages. A seed could wait through drought, survive transport, and begin only when local conditions gave the young plant a fighting chance. That changed the pace and scale of expansion across the continents. Trees and shrubs no longer had to keep their future exposed at every stage. They could send it out armored and provisioned. In evolutionary terms, that was an extraordinary advantage. It helped seed plants spread into habitats where older reproductive systems struggled. Whole ecosystems eventually came to be dominated by plants using this strategy, from conifer forests to dry grasslands and flowering plant communities across nearly every climate zone. Seeds did not merely improve survival. They redrew the boundaries of where plant life could thrive. Flowering plants later turned seeds into astonishing engines of diversity. Seeds existed before flowers, but flowering plants took the idea and unleashed it in spectacular ways. They combined seeds with blossoms that could attract pollinators, fruits that could recruit animal dispersers, and life cycles flexible enough to work in habitats ranging from deserts to wetlands to forest canopies. The result was an explosion of forms, strategies, and species. Once seeds were linked to color, scent, nectar, and elaborate fruit structures, plants could specialize in extraordinary partnerships with insects, birds, mammals, wind, and water. This helped flowering plants diversify faster and more broadly than many earlier groups. A meadow, orchard, rainforest, or vegetable patch is full of that legacy. Hidden inside every fruit, grain, nut, or bean is the outcome of a long evolutionary experiment in packaging the future more creatively. What makes this so thrilling is the scale of success. Flowering plants did not just use seeds well. They turned them into one of the great engines of life's abundance. Fruits evolved partly to tempt animals into carrying seeds away. A fruit is not just a treat. It is an advertisement, a payment, and a transport strategy rolled into one. By surrounding seeds with sweet flesh, bright color, scent, or rich nutrition, the plant attracts animals that will eat the fruit and move the seeds elsewhere. This is one of the most elegant bargains in nature. The animal gets energy. The plant gets dispersal. Over evolutionary time, this led to remarkable pairings between plants and the creatures that feed on them. Different fruits appeal to different dispersers. Birds may respond to color and visibility. Mammals may follow scent. Some fruits ripen when their target animals are most active or abundant. The result is a world where eating and reproduction are tightly interwoven. A berry in a beak or a fig in a bat's mouth is not just a meal. It is part of the plant's plan. The fruit exists in large part because the seed needs a willing traveler. A colorful fruit is often a seed delivery system in disguise. What looks to us like beauty or abundance is often a carefully evolved signal. Bright reds, oranges, blues, and purples can help fruits stand out against leaves and branches, making them easier for animals to spot when the seeds inside are ready for transport. Softness, sweetness, and scent add further encouragement. The plant is not trying to make the fruit attractive in a vague sense. It is trying to make it hard to ignore at precisely the right moment. Once eaten, the fruit's job is largely done. The flesh is consumed, but the seeds continue the journey. That turns orchards and forests into networks of invitations. Each colorful fruit is a message sent into the senses of birds, mammals, and sometimes even reptiles. Come here. Eat this. Carry the future onward. The disguise works so well that humans have built whole cuisines around it, often forgetting that beneath the pleasure lies a highly practical system for moving seeds through the world. Some seeds survive digestion better than the fruit around them. That durability is not an accident. In many fleshy fruits, the edible part is designed to be sacrificed, while the seed inside is built to endure the trip through an animal's body. Acids, enzymes, crushing, and moisture may destroy the surrounding tissue quickly. Yet the seed coat can remain tough enough to protect the embryo until it is released at the far end of the journey. In some cases, passage through the gut may even improve the seed's chances by removing pulp, weakening outer barriers, or placing the seed in nutrient-rich droppings. This creates a striking contrast within a single fruit. One part is meant to vanish. The other is meant to persist. That division of labor makes the whole system work. The fruit attracts the animal. The seed survives the cost of being eaten. It is a wonderfully ruthless arrangement. The meal is temporary. The beginning hidden inside it is what the plant was truly investing in. Elephants, bats, and birds are major gardeners of the planet. They do not carry watering cans or seed trays, yet their feeding and movement patterns shape forests and woodlands on vast scales. Elephants can swallow fruits whole and deposit seeds far from the parent tree, sometimes across impressive distances. Fruit bats move between feeding sites at night and help disperse the seeds of many tropical plants over wide areas. Birds do the same in forests, hedgerows, wetlands, and islands, linking habitats with every journey they make. These animals are not merely consumers of plant life. They are active participants in where plant life happens next. Some trees and shrubs rely heavily on them, and landscapes can change when these dispersers disappear. Regeneration slows. Certain plants struggle to spread. The quiet traffic of seed through animal bodies turns out to be one of the great hidden forces behind the arrangement of living places. Forests are not only grown by roots and rain, they are also planted by wings, feet, and hungry mouths. The seed trade has carried stories, empires, and diets across oceans. When seeds travel, they rarely travel alone in meaning. They carry taste, memory, labor, ambition, and sometimes conquest. A sack of rice, wheat, beans, or spice seed can cross a sea and change what people plant, cook, sell, and depend upon. Entire colonial projects were shaped by the movement of useful plants, as empires tried to transplant crops into new climates and secure control over valuable harvests. But the story is not only about power from above. Families, migrants, and traders also carried seeds in quieter ways, tucked into luggage, hidden in hems, saved from old gardens, or exchanged between neighbors. With them came familiar meals and the hope of rebuilding home in foreign soil. That is what makes seed trade so gripping. It is not just commerce in biological material. It is a movement of appetite and identity. A seed can cross water as cargo, then land as culture, altering both the landscape and the table. Sacred seeds have appeared in rituals, myths, and medicine for millennia. Human beings have long recognized something powerful in a seed's nature. It is small, silent, and apparently lifeless, yet capable of becoming abundance. That alone makes it a natural symbol of renewal, hidden power, endurance, and return. Across cultures, seeds have appeared in offerings, healing traditions, seasonal ceremonies, and origin stories, often standing for fertility, continuity, or the mystery of life emerging from stillness. Some were used in ritual drinks or incense. Some were carried as blessings for harvest or protection. Some entered traditional medicine because their oils, bitterness, heat, or nourishment gave them practical value as well as symbolic meaning. The important thing is not that every culture treated seeds in the same way. It is that so many saw in them more than food or plant material. People noticed the miracle inside the shell. Long before modern biology explained the embryo, seeds were already speaking to the human imagination in religious and healing language. People once wore certain seeds as charms for luck or protection. That habit makes beautiful sense when you think about what a seed represents. It is a natural vessel of survival, a compact promise that life can continue through danger, cold, hunger, and delay. In many places, seeds were threaded into necklaces, sewn into clothing, tucked into pouches, or carried close to the body as amulets. Some were chosen for shape, hardness, or rarity. Others were valued because of the plant they came from, or the meaning attached to them in local tradition. A polished red seed, a dark, dossy bean, or a tough rattle-like pod could feel charged with power simply because it endured. These objects crossed the boundary between botany and belief. They were not planted in soil, but in hope. What is lovely about this custom is that it reflects a deep, intuitive truth. Even without scientific language, people sensed that seeds were symbols of persistence, and they wanted some of that persistence near them. Archaeologists can reconstruct ancient meals from charred seeds in soil. A burned seed may look ruined to us, but to an archaeologist, it can be a small miracle of survival. When seeds are charred in hearths, ovens, storage fires, or cooking accidents, they can become carbonized rather than fully destroyed. That carbonized state helps them endure in soil for astonishing lengths of time. Later, when excavated carefully, they reveal what people were growing, storing, grinding, cooking, or accidentally dropping. A few blackened grains in an ancient pit can point to bread, porridge, beer, or harvest waste. Lentils, millet, barley, peas, and many other seeds have helped researchers reconstruct diets that would otherwise be lost forever. This is one of the most intimate forms of evidence from the past. Great monuments tell us what societies built. Charred seeds tell us what people ate. They carry the trace of kitchens, fields, and hunger, preserved not as writing, but as the stubborn remains of once living meals. Carbonized seeds can reveal farms, trade routes, and vanished climates. Once seeds are preserved by charring, they become more than clues to diet. They can also reveal how a landscape was managed, what people imported, and what conditions once shaped the land. A concentration of one crop might suggest nearby cultivation or storage. Unfamiliar species in a settlement can hint at exchange networks reaching beyond the local environment. Weed seeds mixed with crop remains may show how fields were worked, harvested, or irrigated. Even climate leaves fingerprints. The presence or absence of certain plants can suggest wetter periods, drier phases, warmer intervals, or shifting growing conditions over time. This is what makes archaeobotany so extraordinary. It allows entire lost worlds to be inferred from fragments that fit on a fingertip. A burnt seed from an ancient layer is not just debris. It can be evidence of farming choices, commercial links, and environmental change. Tiny remains become witnesses to worlds that no longer exist above ground. Future foods may come from neglected seeds already known locally. Not every important crop of tomorrow needs to be invented. Some may already exist in local knowledge, grown on a small scale, gathered seasonally, or remembered by communities who never stopped valuing them. Across the world, there are underused seeds from grasses, legumes, and other plants that may offer nutrition, resilience, or adaptability suited to future climates. Some tolerate heat better than major staples. Some grow in poorer soils. Some bring proteins, oils, or minerals that could diversify diets beyond the narrow set of crops that dominate global agriculture today. The fascinating part is that these possibilities are often hiding in plain sight. What one system dismisses as minor or old-fashioned may turn out to be exactly what another era needs. So the future of food may not always lie in novelty. It may lie in paying closer attention to overlooked seeds and the people who already know how to grow, cook, and respect them. Scientists are reviving rare seeds to restore damaged habitats. Restoration is not only about fencing land off and hoping for the best. In many cases, it begins with the careful return of missing plants, and that often means searching for rare seed sources before the last local populations disappear. Scientists and conservationists collect, grow, clean, and store seeds from threatened species, then use them to rebuild meadows, wetlands, prairies, dunes, and other damaged habitats. This work can be painstaking. The right local genetics matter. The timing of sowing matters. The soil conditions matter. Yet when it succeeds, the results can be transformative. Flowers return. Pollinators follow. Soil begins to stabilize. Ecological relationships that seemed broken start to reassemble. What makes this so moving is the scale of hope contained in the process. Restoration can begin not with a massive machine, but with envelopes, trays, and patient hands working with fragile futures. A lost landscape is not always recovered by force. Sometimes it is receded back into possibility. Rewilding often begins not with animals, but with seeds. People often imagine rewilding as the return of wolves, bison, beavers, or other dramatic creatures. Those animals matter, but the groundwork is frequently botanical. Before a place can support richer food webs, it may need native grasses, shrubs, wildflowers, sedges, and trees to return. That process often starts with seeds. They rebuild the physical and biological stage on which everything else depends. Roots stabilize soil. Flowers feed insects. Shrubs shelter birds. Wetland plants slow water and create habitat. Without those foundations, rewilding can remain an idea rather than an ecosystem. This is why seed collection and sowing are so central to many restoration projects. The most visible success may come later, when animals arrive or increase, but the first real change often begins quietly at ground level. A handful of native seed can start the recovery of structure, food, and seasonal rhythm. Before the wild becomes audible again, it is often planted. Even a pavement crack can become a seed's unlikely kingdom. A city surface seems like the opposite of fertile ground. It is hard, hot, compacted, and designed to exclude life. Yet seeds are astonishing opportunists, and a narrow crack can offer enough dust, moisture, and shelter for a beginning. A little soil gathers. Rainwater lingers. Wind delivers organic matter. Then one seed settles into that tiny opening and tests its chance. If it succeeds, the effect can feel almost rebellious. A stem appears between stones. Leaves spread where only grit seemed possible. Over time, roots pry wider space from what looked permanent. This is not merely a charming urban detail. It is a reminder of how persistent plant life really is. Seeds do not need grand landscapes to begin their work. Given the smallest foothold, they can challenge concrete, outweigh neglect, and turn accident into habitat. Even the built world is never completely sealed. Somewhere, a crack is enough for life to start pressing back. The quiet power of seeds is how plants learned to outlast time. A seed solves one of life's hardest problems. How do you continue when conditions are wrong, distance is great, and danger is constant? The answer is not speed, teeth, or flight. It is patient resilience packed into a form small enough to travel and strong enough to wait. Through seeds, plants learned how to send life forward through drought, frost, fire, salt, darkness, and the passing of whole seasons or longer. Forests, farms, orchards, grasslands, and gardens all depend on that invention. So do many human histories, meals, and memories. What makes seeds so moving is that their power rarely looks dramatic at first glance. They sit in the hand as stillness. Yet inside that stillness is timing, inheritance, survival, and astonishing possibility. A seed is not loud about what it contains. It does not need to be. Its achievement is written everywhere. Plants live. They found a way to endure by carrying the future in silence. As our journey through seeds comes to a close, it is lovely to pause and notice just how much was hidden inside something so small. We wandered through ancient tombs and Arctic summers, through deserts waiting for rain, through forests planted by birds and squirrels, through oceans crossed by coconuts, and through fires that somehow make way for new life. We followed seeds that spin, float, burst, cling, sleep, and endure. And all the while, the same quiet truth kept returning. Inside these tiny forms, the future waits with astonishing patience. It is strange and comforting to think about. A seed can rest in darkness for a very long time, asking nothing, holding everything it needs until the moment is right. Then, with water, warmth, or time, it begins. A root turns downward. A shoot rises upward. And something that once looked like dust or stone starts to remake the world around it. So now, As your own day begins to loosen its hold, perhaps you can let that feeling settle in. Let your thoughts drift like wind-carried seeds. Let the weight of the day sink softly away, like an acorn finding earth. There is no need to hold on tightly to anything now. You can simply rest here for a moment, in that calm space between waiting and waking. And if you happen to still be awake, there will be another video waiting for you on the screen, ready to carry you onward into another quiet corner of science. And if not, then let this be where the night gently takes you. Thank you for spending this time here with me. And if you enjoy these slow wandering journeys, you can like, subscribe, or leave a comment below. Sleep well, and good night.